Morning, good afternoon, good evening. I am Justin Joss. So I'm here to present a topic of dual band inverted antenna with a trap-based technique. So before coming to the topic and the details, let me introduce myself and my team. So along with me, I'm working as a RF engineer in Honeywell, and my team includes Prasad Samudrala. He's an architect, and Amit Kulkarni is a director of engineering. So we in Honeywell, we are part of the Honeywell Building Technologies group, where we design and develop new products, like especially in buildings, the devices like thermostats, wall modules, and fire-based devices and security-based devices, plant controllers. So various wireless devices which is used in smart buildings, and that is what our group, our division is working on. Yeah. So let me come to the topic. So this is basically an inverted F type of an antenna, which uses a particular technique called trap-based technique, which achieves dual resonance for the sub GHz bands. That is 900 megahertz band and 868 megahertz band using a single antenna. So that's what I put the word as small band separation, because the two sub GHz bands are closely related, closely separated. So here are a few of the contents. I'll introduce about the topic, and I just pass through various inverted F configurations and we'll compare F among them. And we'll talk through different methods of improving the bandwidth of an antenna, and we'll explain in detail what is our design methodology, and we'll pass through various simulations and the results, and we'll discuss. So here is a general inverted F antenna. So this is I would say we'll compare with respect to this, and we'll walk through this presentation based on this. So maybe some of you might be familiar with this antenna, or maybe new to this, no problem. So let me just take a present pointer. Okay, so this is an antenna structure here. This is basically a PCB based antenna. As you can see, the green color is showing a PCB. The substrate is FR4 substrate. So this is an antenna, and these rectangular sections on the left and right is a ground, and this middle point, that is a feeding line where the power is fed to the antenna. So this is a matching, you can say white box here, that's a matching section to match the impedance of the antenna to properly to 50 ohm impedance. Maybe we'll go into the details in the coming slides. As you can see, lambda by 4, that is the overall length of the antenna. And on the right side here, you can see the below this dotted lines is a ground. This is a grounding area in the PCB, and above that dotted line there is no ground, because that's a clearance for the antenna. So basically, this is an antenna keep out zone where we will not be keeping any ground, because that will affect the ground, neither ground nor metal parts, because that will affect the radiation performance of the antenna. So here we have the antenna, the feed line, and ground. These are the major components which are part of this structure. So this is some real PCB images just to compare what are the various antenna configurations. Here I am just taking inverted F antenna as a common reference for comparison. Among the inverted F antenna, what are the various geometries? I mean to say, say the first image, that's why I put the caption as PCB antenna versus external antenna versus metal stamp antenna. So external antenna, as you know, typically I've not included that in the image here, because most of us are familiar. If you see the Wi-Fi routers, that antennas which is seen externally, that's the external antennas. And the first image here shows the metal stamp antenna. As you can see here, this is actually like it is not. It is kind of standing on the PCB. Okay, and it's basically a metal. And the right one is, this is actually printed on the PCB. So that's basically a PCB based antenna. And this image on the bottom is also a PCB based antenna. The difference is this image, left and right image differences, both are PCB based antennas, but the left one is it's a normal inverted F type of antenna with a single bend here, but this is called a meandering inverted F antenna. Basically this kind of geometry is called meandering. That is to achieve shorter length by meandering. That is what the meandering antenna. So basically we have PCB based antennas and metal stamp antennas shown in this image. In most of the application, be it a mobile, be it any consumer electronics, any mobile devices, any fixed wireless devices, in most of the cases, we go for this PCB based or printed antennas because that is very cheaper, that consumes less space, and ease of fabrication. So because of that, we prefer PCB based antennas, because metal stamp antennas, that will increase the overall the thickness or the height of the device, because this occupies that much area in the air, right? So, and the fabrication is also costlier. So PCB antennas are generally preferred, and this is some of the features of the inverted IFM meant as inverted F antennas. So this is having a compact form factor, because it's we have got different techniques like meandering and other techniques to reduce the overall size of the antenna. So we can achieve compact form factor with this design of this type of antenna, and this is generally called, as in the previous slide, if I go back, this is called a lambda by 4, you can see, right? That is nothing but a quarter, 1/4 of the wavelength. So that is why it's called a quarter wavelength type antenna. And this is about the pattern coverage. So this antenna is actually radiating in all directions. That is called, it's called omnidirectional antenna, and it's having a good efficiency. So to improve the bandwidth, so if you take any antenna, be it horn, reflector, patch, any antenna, bandwidth is a critical factor, because nowadays we go for n number of devices, each person having multiple wireless devices. If you take a building, if you take a campus, a college, whatever it is, n number of devices are there, right? So bandwidth is a crucial factor, and but bandwidth is limited because we have spectrum limitations and we have huge number of devices occupying the spectrum. So we are always looking for what is a method to improve the bandwidth. That is actually lies in the geometry or the design. So in this particular case, if you vary the height of the antenna, it will we can improve the bandwidth. The spacing between the feed line and shorting line means, if I go back, uh, this is a feeding line and this is a feeding line, this is a shorting line. So if you vary this spacing also, that can also impact or improve the bandwidth and the trace width of the antenna trace. So these are some of the design factors which would help us to improve the bandwidth of the antenna in general case. So let's come to the design details of this particular presentation. So this, as you can see, this is a normal inverted F antenna, this structure. Here, this bottom is the ground of the PCB. So this particular structure is shown without an enclosure for this analysis and design. It uses a 100 by 100 PCB based dimension of the PCB. Overall dimension of the PCB is 100 by 100. Whereas the antenna area is, the second image is actually the details of the antenna, more details of the antenna. First image is antenna with the ground is shown here. Let's go to the second image now. So as you can see, this is the overall length is 59.4, and the height is, this is 11 millimeters. Please note all the units and millimeters. So generally we go for millimeters as a standard unit here. Yeah. So, here the key point is, as I shown in the first image, this is a shorting point. This is a ground, right? So these are all metal, and this green color area is a substrate. Means nothing but it's a dielectric. So this is shorted to the ground. This is a feeding point. So this red color triangular component, that's a feeding. Nothing but we giving the power supply to the antenna to excite the antenna, thereby it radiates. So our objective here is design goal is to if you design a single inverted F antenna, that will achieve a single resonance, or it will radiate a single point of frequency, say 868 or 915 megahertz. But here with this single antenna, we want to achieve both radiation, both resonant frequencies, 868 as well as 915. So that is, for that we are adding this trap based technique. So trap is, I'll go to the details in the next slide. So before that, let's go to the design equations, how we arrived at the particular the structure. So as I mentioned earlier, the left first arm is shorter to ground, and then there is an opponent, right? If I go back here, see this shorting point, and this is an opponent. So general we see that, that impedance, if you relate that impedance at open point, its impedance is infinity, and shorting impedance is 0. So that same methodology, or same what to say, same analysis is used here for this equation framing. So Z1 is an impedance at this point, say that is 0, because that is, so this is an equivalent electrical AC circuit representation for the antenna. Shorting point, it's represented by an impedance of Z1 equal to 0, and the right one, Z2, is the open end of the antenna, which is equal to infinite impedance. And this is the overall length is divided into two halves, like L1. As we see that overall length of this inverted F antenna is lambda by 4. So first part length is lambda 1 L1, then second part will be lambda by 4 minus L1. Okay, and so this is the input section where the feeding is given, right? So this is a equivalent representation, electrical equivalent representation of the antenna. And if you go to this equation, some of you might be familiar with the propagation constant. So that is called represented by gamma. Gamma is a propagation constant. So let me introduce the variables. This omega is the angular frequency, that is nothing but 2 pi f, and epsilon is the permittivity of the medium. C0 is a velocity in free space, and this length of the antenna. F is a frequency. F is a frequency. So these are the various terms. So once we know this is an inverted F antenna, so it's lambda by 4 is the that value we know in the design. So once we get the lambda by 4, we can know what is the frequency, because frequency, velocity, C equal F lambda with the relation velocity, frequency, and wavelength are related. Then once we estimate the frequency, we can calculate the length of the antenna and also the propagation constant. So why we go for the propagation constant is I'll explain here. So if you know the quarter wavelength, like lambda by 4, you get the frequency, then propagation constant can be estimated using this equation, right? Then then once the propagation constant is available, we can calculate the input impedance. So then so from this we calculate the input impedance. So yeah. So consider these two as two kind of parallel branches. Consider standard inverted F antenna, 2 branches. One leg is shorted, the left one is shorted, and the other one is open. So considering these two legs, these two sections in parallel, there is a standard input impedance equation for the circuit impedance point, right? Input impedance. So using that standard impedance equation and taking these two assumptions, that two sections are in parallel, we can come to a equation that this is a derived equation. Input impedance is equal to E0. This is a characteristic impedance of the transmission line, the particular line. It's a cot h of gamma L1 plus tan h of gamma lambda by 4 minus L1 all to the power of raised to minus 1. So we know gamma, then from gamma what we estimated earlier, we got input impedance. So if you know the input impedance using a LC matching network, inductor and capacitor network, we can properly match the input impedance. So that's the all idea of what is this equation and what is the representation. In short, using the propagation impedance. So if you know the input impedance, and if you know the what is output impedance, it should be matched to 50 ohm. So then using Smith chart, we can properly match it. I'll explain that in the coming slides. So the particular features, some unique features about this design is this is single antenna which covers NA. NA is a North American region and this is a Europe region. So if we go to these last points, see 865 to 868 is a European band. European sub GHz frequency band spectrum is only 5 megahertz. And whereas for the North America, this is 900 to 930. To be precise, it's 902 to 928 megahertz. So that's a North American sub GHz frequency spectrum. So this antenna in short covers these two spectrums using the single antenna, using the trap-based concept. And this is using a FR4 based substrate, so it's a cheaper solution. Yeah, so let me explain what is that trap functionality here. So there are two possibilities of implementing the trap. So you see the tiny section here, right? So there is a small gap here. So in this section is at the midway bit on this antenna length. That's why I put it as trap at midway. And in the bottom one, the second image, the trap is at the opponent. So here, if I just go back here, you see this is 868 and this is 900. So the band separation is approximately 30 megahertz, right? So that is band separation is 30 megahertz, means the two different bands are closely separated. So that means because of that, if you keep this trap at the open endpoint, the tolerance. Tolerance means trap is nothing but it fundamentally uses a combination of L and C, inductor and capacitor values. So inductor and capacitor, as we all know, there is a tolerance effect for each inductor and capacitor. Even if we choose suppose a 2 picofarad capacitor and 3 nanohenry inductor, practically due to temperature and other variations, we won't be able to get exact value. So there'll be some that is a tolerance what we specify. And because of tolerance variation, the effect of the realistic effect, what we get, even if we choose 3.1 nanohenry, we might get the effect of a 2.8 nanohenry because of the tolerance. So because of that issue, and since the two bands of interest are separated by a very small gap, this kind of a configuration at the open-end trap will not be suitable. This we come to a conclusion based on our simulations and design. The results we'll discuss in the coming slides. So based on that results, and we have concluded that if you keep the trap at the midway, it will be more suitable in this particular design to achieve the dual band. Okay, so from here onwards, we are entering the results section, and we'll be discussing detail what each sections are meaning. Okay, so these two images are showing. One is at 0.866 gigahertz, nothing but 868 megahertz, and this is I'm just choosing the center frequency of both the bands. This is a European band center frequency, and this is a 915 megahertz. That's the North American region. So this is a current flow across the antenna element. And just for information, I'm using the software called CST for the simulation and design here. Yeah, so continuing here. So as you can see, this is a shorting and this is an hour length of the antenna. This is a feeding line and this is a grounding section. So as you can see, this is a strong current flow across the antenna at 866. And similarly at 915 also, we can see kind of a thick or strong current flow. That means it radiates. Proper current is, we feed the power supply and the current is properly flowing through the antenna. If the antenna efficiency or radiation is not proper, we won't be able to see that what to say, high density current distribution across the antenna. It might be radiating, it might be flowing across other surface. So if you see that this indication on the right, this is showing decibel scale. This red is nothing but it's a stronger intensity, 0 dB, going down yellow, green, or lower. So as you can see, this is you can see red, green sections here. It means more strong. That's why I written a strong current flow across the antenna. That means it radiates efficiently at this both the frequency bands. So this is about the trap section. So I just put a two-port network here. This is the actual trap section, what I meant used in the antenna. It uses a LC network combination, as I mentioned earlier. In the L value, inductor value, the capacitor value is 9.1 picofarad, and inductors, I use two inductors in parallel. That is also to take the effect of the advantage of the tolerance, to get less tolerance effect from the inductance. I used two inductors in parallel. This is 6.8 nanohenry in parallel with another 6.8 nanohenry. LC value from the, if you know the L and C value, we can calculate the resonance frequency of the circuit, whatever may be the circuit. So using the equation 1/2 pi root LC. So if I calculate that with these values, it comes to around 904 megahertz. That means our band of interest in the NA region is North America is from 900 to 930. So 904 lies in that region. So if we come to the right side graphical representation here, this is called an S21. S21 is nothing but S parameters is kind of the common representations in RF. And if you have two network 1 and 2 ports, it's called S21, right? It's like it's kind of a power equivalent representation. What the power is flowing from port 1 to port 2. So this is an S21 representation of this LC network or the trap used here. And this LC network is acting like a stop band filter. And nothing but it would stop band. You know, we might be you might be familiar with the stop band filters, pass band filters, all pass filters. So this LC network will act as a stop band filter for the high frequency. High frequencies like the higher harmonics or something above 1 gigahertz, because our area, we need only the radiation to happen at 900 megahertz and 868 megahertz. Something other higher can be blocked. So that is one of our objective here. And if you notice 3 graphs, this is actually 3 graphs is just for comparison. Let's focus on the green color graph, the center one. This is, you see, I put the values 9.1 picofarad here and 6.8 nanohenry, right? So that I just use nearby values of 9.05, 9.15 for comparison. If you see this 9.1, this combination of a trap here, this is centered at 904. As I said, if you calculate the resonant frequency using this value, it comes at 904. That is why this is a resonance, right? This deep value, 904. And it have a value. So when we look the S21 value or S11 value, generally we should look for the bandwidth is considered below the minus 10 dB. So this is properly resonating at 904, and we have a wide bandwidth below minus 10 dB. So this reference is with this value. That means we see that it's have a proper resonance at the 900 megahertz band. So we need to cover the 860 also. So with the trap and using the antenna lambda by 4 length, this is the return loss. So if I just go back here, we have the 900 band coverage from here using the trap network, and using the antenna length, this is a return loss. So return loss is a very crucial, one of the crucial parameter or result what we analyze, and what we, based on this, actually we are tuning or antenna matching. So if you observe here, return, just for information, return loss, we take minus 10 dB as a standard. So the value of the return loss should be below minus 10 dB. That value is taken or called the given as a bandwidth of the antenna. So if you see the green color graph, that is our design value here. The green graph, see, as I mentioned, in the Europe band, it's from 868 to 870. So that is actually well below minus 10 dB. And if you take the 900 in North American band, it's again from 885 to say 940 approximately. So that means the summary here is this green graph, right? It's from 890 to 940 approximately with respect to minus 10 dB. So that means with this graph, we are able to say that the antenna, this inverted F antenna with the trap concept, is covering the spectrums in the Europe band, well in the Europe band from say 860, beyond 860 actually. We need only this much band in the Europe. So we have a coverage from 855 to 880. And North America also we have wide coverage. So so we have a very sufficient or wide bandwidth both in the Europe and North America using a single antenna using this concept. So that is the first proof of the design objective here. Yeah, and please just don't confuse with the LC network here. So LC network for matching, using in the matching network also we use LC network for impedance matching, but that we use the LC network in the feeding line section. Here actually use not in the feeding line section, the LC network is used along with the antenna. So that is a difference. Just don't confuse with people who are familiar with matching and this concept. So Smith chart is, I mentioned previously that we'll discuss on the impedance matching the previous next slide. This is a point. So in Smith chart is what we talk about the impedance matching. In RF, 50 ohm is generally taken as a standard because of the power and insertion loss, right? Because of those factors, we have taken 50 ohm as a reference standard. So we always look to match our antenna, whatever RF circuit we take, power amplifier, linear amplifier, filter, whatever it is, right? We always try to match the impedance. If the impedance is not properly matched to the 50 ohm, due to impedance mismatch, it causes the loss in the circuitry, reduce efficiency. Okay, so so that is why this is nothing but, if you see, 50 ohm is the center point here, corresponds to center point. So using Smith chart, say this I put markers at 866 and 901. Two markers, the value, it should be the impedance at those points should be close to. Hey, how still am I audible? Right. So at 866, you see 48.6, and this is a real part, and like we say R plus JX. So real part, and this is imaginary part. Imaginary part is minus 1.56. That means at both the frequencies of interest, the imaginary part is close to 0 and real part is close to 50. That means this is again a design objective. That means our frequency band should be close to 50 ohm. Real part should be close to 50 ohm, and imaginary part should be close to 0 ohm. So that is what Smith chart, right? So here with Smith chart, we are proving that we are properly matched to 50 ohm at both the frequency bands of interest. So we had the proper return loss, we had this proper impedance matching using Smith chart that we prove. Then going forward, this is the radiation pattern. This is the next parameter of this antenna. So this is a three-dimensional pattern, which see, this is a structure shown in like a invisible inside. The pattern, as you can see, it's covering almost all the directions. So that is why it's called omnidirectional coverage, omni 360, right? So 360 is an ideal case, but practically it won't be 360 because of metals and because of reflections and because of not 100% efficiency. Obviously, it won't be 360-degree coverage, but it's kind of a partial omnidirectional or quasi omnidirectional pattern. So we have a proper pattern, and there are various factors to analyze here. This is called the realized gain of this antenna. It's called 1.762 dBi, and this is a total efficiency, system total efficiency. It's minus 0.6 dB. So it's nothing but when you translate that the normal scale, it comes around more than 80%. This is in decibels. Because in RF, most of the values we represent decibels, because of the values are, if you say very higher value in normal scale can be easily represented and what is manipulated easily in the decibel scale. So that's why mostly our decibel, beat power, efficiency, gain, everything we represent in dB or dBi scale. So this is at 868, 866, and this is at radiation pattern at 915 megahertz. Similar results. Here the gain is different, 2 dBi, and having an omnidirectional pattern. Yeah, so this is called the far field pattern, far field radiation pattern. I'll just quickly go through various parameters. Far field pattern. This is a frequency. This is a efficiency in dB and gain, and this shows the intensity of the scale, right? This you can see red color here most of the case. That means its radiation is proper. And this is a two-dimensional equivalent of what the previous slide shown. Just for ease of understanding, as you can see, this is kind of a proper pattern with some dip here. That dip is actually what we say some nulls or something, because of the practicalities. We only having a full circle, right? So this kind of things happens. This is what we need to read out here is, so what is we need to analyze what is the pattern. This is at various cut angles are there. This is an angle called phi equal to 90-degree cut plane. We have got various cut plane, right? Theta, phi in the Z. And this is frequency, and this is a main lobe direction. What the main lobe is in the 5-degree direction now. And this is the beam width, like the angular width in 3 dB beam width is called 100-degree, 100.7 dB beam width. And this is a 2D radiation pattern at 915 megahertz. We have the similar results, frequency, angular beam width we can read out, and the radiation main lobe direction. So this is a 2D radiation pattern. Okay, just coming to the result summary. What we discussed in the previous slides, across the results, various slides. So in summary, in the 868 megahertz band, we have a bandwidth of more than 20 megahertz. If you recollect, it's from 865 to 870 is a band of interest. That is 5 megahertz is our objective, but we have more than 20 megahertz. It's well beyond our objective, more than 4 times. It's always good. And 915 in the North American band, we have 30 megahertz is our design objective, but we achieved more than 50 megahertz. So that is on the bandwidth part. And on the efficiency, we have over 80% efficiency. Typically, we need, or generally efficiencies of varies in the order of 50 to 70 when we do the measurements. So in the simulation, we have more than 80%. And the gain, the realized gain is coming to be 1.7 dBi for the 868 band and 2 dB approximately for the 950 megahertz band. So that's on the bandwidth, efficiency, and realized gain results for this particular antenna design. And coming to the conclusion, so I just put us main 4 points here. This is a compact inverted F antenna with a design for dual sub-GHz bands for the Europe and North America. The dimension is compact because of the trap-based concept, and we have a very wide bandwidth here. We have more than 20 megahertz in the Europe band, and North American band we have more than 50 megahertz. The pattern is, it's called quasi omnidirectional. I mean to say, it's not exactly 360 degree being practical case. It's approximately 360 degree, but we ensured that there is coverage in all angles, almost all angles. Hence, it's called quasi omnidirectional pattern, and we have a very surplus amount of efficiency here, more than 80%. So efficiency is nothing but you can say higher the efficiency, we get better radiation. If dependent factors, we need to have proper impedance matching, input impedance matching. That can give better efficiency. That is one of the factors. Here we have, as we see in the Smith chart, we have proper impedance matching close to 50 ohm. That is also one of the factor which give better efficiency. And coming to the application part, so this design we are using in one of our products. As I mentioned, we are using various wireless devices. We are developing various wireless devices to use in buildings, like IoT based devices. So this kind of a design comes in our one of the products which work both in the North American band. That is on the application or use case part. I just put some of the references for putting some of the images here. Yeah, that's it. With this, I end my presentation. So thanks for the time. Any questions?